Welcome back to another episode of the organic chemistry course, hydroxy compound. Okay, hydroxy compounds, we're just talking about alcohols. Okay, so alcohols are also classified into three groups: primary, secondary, or tertiary alcohols. Primary alcohols are referred to as first degree alcohols, and secondary alcohols as second degree, and tertiary alcohols as third degree alcohols. So I think let me reiterate what I mean by primary, secondary, and tertiary alcohols. So here, this is the hydrogen atom over here. You see the carbon atom here that is attached to the OH group here. OH group is attached to two hydrogen atoms, 1 and 2, in one other group. So if the carbon attached to the hydroxy group is got one other group, it is a primary alcohol. Second, this one is secondary alcohol, in that it is the carbon atom attached to the OH group is attached to one and two other groups. In the tertiary alcohol over here, the carbon attached to the OH bond is attached to 1, 2, and 3 other groups, right? That's all. That's all you should know. So here in the notes I was saying, alcohols are classified into according to the number of other groups, right? Primary alcohols, one other group. Primary alcohols, one other group. Secondary alcohols, two other groups. Tertiary alcohols, three other groups. That's all I mean to say there. Reactions of alcohols. So as far as alcohols are concerned, in these notes, I used ethanol as a typical example for the reactions involving alcohols. One of which, number one, we have combustion. Alcohols burn in the presence of oxygen to produce carbon dioxide and water. So it's just you put your alcohol plus your oxygen, you produce your products, carbon dioxide and water. It's just a matter of balancing the atoms. In the next type of reaction that alcohols undergo are substitution reactions. Alcohols react with px3 and px5, where X here can either be chlorine, bromine, or iodine, right? In a substitution reaction. So in this case, in this reaction here, they used chlorine as my X, right? We've got ethanol can react with PCl3 to produce 3 moles of chloroethane, right? And POH3. POH3 is also another example of H3. PO3 is the same thing, right? And ethanol can also react with PCl5 to produce monochloroethane, POCl3, and HCl. So all these are white fumes, guys. White fumes, the HCl here and this one, these are just white fumes. That's what I written in the obscured words there, white fumes. And if you use SOCO2, remember, I meant SOX2. It can be chlorine, bromine, or iodine, right? This is the reaction. Try to memorize the equations, guys. They hope you understand what's going on. Then the third type of reaction, reactions with sodium. Alcohols react with sodium to undergo a redox reaction. So what happens there? A sodium salt is formed plus hydrogen gas. The above reaction is a metal-acid reaction and leads to the formation of white compounds. The white compound is the sodium salt that we have here. It is a white compound. So oxidation to carbonyl compounds and carboxylic acids. So let's talk about primary alcohols. Primary alcohols are oxidized into aldehydes, and then into carboxylic acids by acidified K2Cr2O7, which is by acidified potassium dichromate 6. So this is the reaction. Ethanol here reacting under reflex conditions with that potassium dichromate 6 producing an aldehyde. Further oxidation oxidizes the aldehyde into a what? Into a carboxylic acid. Acidified potassium manganate oxidizes primary alcohols directly into carboxylic acids because it is a stronger oxidizing agent. It is a strong oxidizing agent. I hope you understand. So if you use KMNO4, this stage here becomes eliminated, right? Then you produce your carboxylic acid right away. Secondary alcohols on the other hand, secondary alcohols are oxidized directly into ketones by either of the two oxidizing agents. So here you've got your ketone being your secondary alcohol, right? Which is attached to one to two other groups being oxidized to what? To a ketone. That's all. Tertiary alcohols, on the other hand, resist oxidation. They are not oxidized in any way, right? So that's what there is to it. Now about alkenes, as far as alkenes are concerned, is that the other type of reactions that alcohols undergo. They also can also undergo a dehydration reaction to form alkenes. A good example is when you add concentrated sulfuric acid at 170 degrees Celsius. Concentrated sulfuric acid is known as a dehydrating agent. It removes water from from substances. So at these conditions, this is the most common equation, right? It dehydrates the molecule into an alkene plus water. Other conditions that can be used for dehydration of alcohols are heating the alcohol in the presence of aluminum oxide or silicon dioxide to produce the alkene in water. Right. So in these reactions that I'm presenting, be mindful of the reaction conditions, guys. The reaction conditions, because these are some of the things that are asked in the exam. Esterification. Alcohols react with carboxylic acids to undergo an esterification reaction in which an ester is produced. It is recognized by a sweet smell. Esterification is acid catalyzed. So here you've got alcohol plus your carboxylic acid reacting to produce your what? Your ester plus your water. That's what there is to it. Right? Moving on. So here are just characteristic distinguishing reactions. How you can distinguish the alcohols experimentally in the lab. For example, I just gave two different ways. Here, let me just read it to you. To distinguish between the classes, to distinguish between the classes of alcohols, acidified potassium manganate is added to a solution of the alcohol. The mixture is warmed, right? Decolorization is observed for primary and secondary alcohols, but not for tertiary alcohols, right? So if you find out that let's say you've got three samples of these three different alcohols, then you put acidified potassium manganate 7. The sample that is not decolored, that does not show a change in color, that is the tertiary alcohol, right? Now, in the next step, this component that is called 2.4 dinitrophenylhydrazine. If it is added to the resultant mixture, an orange precipitate is observed. If the is observed, an orange precipitate, this species 2.4 dinitrophenylhydrazine, it is used to test for carbonyl compounds, right? If remember, when you added acidified potassium manganate to the tertiary alcohol, we said there will be no decolorization, right? But if there's a primary and secondary alcohol, right, both of for the primary it's oxidized directly to a carboxylic acid, and with secondary you've got the aldehyde, the ketone. For sorry, you've got the carbonyl, the ketone. So they are saying an orange precipitate is observed of 2.4 dinitrophenylhydrazine is observed if the alcohol is a secondary alcohol, but no precipitate is observed if the alcohol is a primary alcohol. I'm going to touch this on the next topic. That's why I indicated there to say C carbonyl compounds. Okay, that's all. And how to test for different how to test for carbonyl compounds. Let me read out to you the next, the alternative method, right? They were saying that an alternative method from the one suggested is to warm the alcohols with acidified potassium dichromate 6 and to collect the organic products by immediate distillation. For both primary and secondary alcohols, turn acidified potassium dichromate 6 from orange to green, while tertiary alcohols have no reaction. If a primary alcohol is present, the distillate obtained is an aldehyde, which can be identified by reacting with blue Fehling's blue solution yielding a brick red precipitate, or with Tolen's reagent to give a silver mirror. I'm going to touch about these topics in great detail. We are saying what they are saying there is to say, if we've got an aldehyde, then you put Fehling's blue solution, a brick red precipitate is observed, right? And if you've got an aldehyde and you place what is called Tolen's reagent, a silver mirror precipitate is observed. Now, in the same way, you've got the primary alcohols. We said they're oxidized to ketones, right? They don't either Fehling's blue solution or a Tolen's reagent. But the ketones give an orange precipitate with what? 2,4-dinitrophenylhydrazine. I hope you got it. But even if you did not get it, I'll be talking. I'll be covering on these type of reactions with involving carbonyl compounds, aldehydes, and ketones in the next topic. Is the one that I'm referring to here to say C carbonyl compounds. So methyl alcohols. What are methyl alcohols? These are alcohols. These are alcohols in such a way that they've got a CH3 group attached to a carbon atom, which is attached to an OH group, right? That's all. That's a methyl alcohol. So methyl alcohols react with alkaline iodine, produce a yellow precipitate of CHI3. So in the reaction that I gave you, that I'm giving you up there, here it's I have my methyl alcohol plus 6 OH negative plus 4I2, giving my carboxylate ion plus my CH3 plus 5I negative plus 5H2O. That's all. Then the equation becomes balanced. A typical example now, for my OH ions there, I put sodium. So the negative ion that I had here was compensated by the sodium, and also for the iodide ions here were compensated by the sodium again, and the atoms became balanced. Move on. Now let us move on to phenol and the chemistry of phenol. The chemistry of phenol is exemplified by the following reactions of phenol. Reactions with the bases. Phenol is acidic because it reacts with the bases to undergo a neutralizing reaction in which a salt and water are produced. But you know the phrase acid plus base, salt and water, right? So you've got your phenol here reacting with the sodium hydroxide to produce your phenoxide salt, sodium phenoxide, which is said to be a white compound over here plus water, right? That's all. Reactions with water. Phenol reacts with water to produce a phenoxide ion, right? To produce a phenoxide ion. Phenol is more acidic than water because it is capable of protonating water. That's what makes it acidic. It is able to donate a what? Proton. Why is phenol acidic? So what happens here is this. Phenol is acidic because the oxygen atom has p orbital electrons, right? P orbital electrons, which interact with the pi electrons in the ring, causing them to be delocalized in the ring. The oxygen atom develops a partially positive charge and pulls electrons away from the hydrogen atom, causing the OH bond to become weak, and an H plus ion is lost easily. Another way to look at it, an easier way to understand what I'm saying is this. The benzene ring here withdraws electrons from the oxygen atom, which becomes partially positive and begins to withdraw electrons from the hydrogen, weakening the OH bond. That's all. So we're saying if the electron density of the oxygen here is very, very is a deficient is deficient of electrons, it weakens the OH bond, right, making it weaker. So it is able to lose a proton more easily. That is how you explain the acidity of phenols. Now another reaction is the reaction of phenol with sodium. Phenol is acidic, so it reacts with sodium in a metal acid reaction to produce a salt and hydrogen gas. And this salt as well is a white compound. The above reaction is a redox reaction, metal acid reaction altogether. And also, phenol is a weak acid, so but it cannot liberate carbon dioxide, CO2 here, it's CO2 there, CO2 from carbonates. So say we know that we've got base carbonates. We usually know that if we say acid plus base carbonate, acid plus base carbonate. Let's say it's a base carbonate, right? It's a base carbonate. It's a base carbonate. It produces a salt plus CO2 plus H2O. But phenol is a weak acid. Now phenol is a weak acid. It cannot produce this kind of reaction. That's why. It cannot produce carbon dioxide, liberate carbon dioxide from what? From carbonates. Nitration of phenol. Phenol now, remember the OH group from, if you look at the OH group from my hydrocarbon lecture, the phenol group is an activator. It causes substitution to take place on the what? Number 2, 4, 6 positions, or the ortho or para positions, right? So if we use concentrated nitric acid, polynitration takes place, right? Multiple nitration. Now, what is nitration? Nitration is just an example of an electrophilic substitution. That's why you see the substitution taking place at the ortho, para, ortho positions here to form 2,4,6 trinitrophenol. But on the other hand, if you use dilute nitric acid, mononitration takes place. The mononitration takes place on the ortho and para positions only. Either you produce this one or this one. But it's usually the case that the para positions are most stable. So you have more of the para substituted compound than the ortho substituted compound. Now let us talk about bromination. Bromination. Phenol reacts with bromine to form tribromophenol. No acid catalyst is required. A reaction like this. Phenol is also a typical example of a substance that is capable of decolorizing bromine, right? 2-bromophenol is a white precipitate. This one, the white precipitate. In this reaction, bromine is decolorized. So that's a takeaway for you. You're supposed to know that, right? So phenol is more reactive than benzene. They are saying phenol is more reactive than benzene, right? Phenol is reactive because it has a lone pair of electrons on the oxygen atom which interact with the pi electrons in the ring, causing them to be delocalized in the ring. The ring becomes more negative, thus becoming more reactive. In other words, the OH bond, benzene withdraws electrons from the OH bond, making the benzene ring more negative. That's why phenol is more reactive. That's the best way I find easy for me to look at it. Now let us go to the next subheading, where we're talking about the relative acidities of phenol, water, and ethanol. Phenol is the most acidic here because it is capable of protonating water, right? Number 2, water is more acidic than ethanol. Why? Because ethanol is an ethyl group which pushes electrons towards the oxygen atom, right? The oxygen atom becomes rich in electrons. I will explain that. Becomes rich in electrons and will not pull electrons away. The hydrogen bond and the OH bond becomes more stronger, and thus difficult to break. Because if you look, let's go back to the chemistry of phenol. We said the benzene ring here withdraws electrons from the phenol, making the oxygen atom electron deficient. If the oxygen atom becomes electron deficient, the OH bond becomes weaker. But alkyl groups on the other hand, alkyl group like this one, alkyl groups have a positive inductive effect on the nitrogen atoms, on the nitrogen, on the oxygen atom, they push electrons towards the oxygen atom, making it electron rich. When it becomes electron rich, it does not weaken the OH bond. Rather, the opposite happens. The OH bond becomes stronger and it becomes difficult to break the OH bond. So that's why alcohols are not acidic. So this brings us to the end of our hydroxy compounds episode. Thank you guys for watching all the way to the end. I hope you found this video helpful, and if you did, please help support the channel by commenting, liking, and subscribing, and I'll see you all next time. Thank you.